So good morning. I hope everybody is doing well today. I sent you an email yesterday about the final exam, right? So I hope that you received it, right? Okay. So we will have our exam next week on Friday, May 6th, from 2 to 5 p.m. It's going to be a 2-hour exam, actually, as far as the questions are concerned, but we reserved a block of extra 60 minutes so that if people want to continue or check their work, double check it and so on, they'll have an opportunity to do so. Okay. So today I'll start by continuing the proof of the linked-cluster theorem. Okay, so as you know, we are in the middle of the proof. We are interested in showing that the nth order correction to the wave function can be obtained by considering the linked diagrams from the principal term. And then the consequence of this statement is that if you write the correction of the energy in order n plus 1, then we end up with connected diagrams that originate from the principal term. Okay, that's how MBPT corrections to the wave function and energy should look like. We haven't proved it yet. Okay, but we already we know through examples at least that those are the results we can anticipate. Okay, so what we did so far is this. I should also say that, maybe remind you that last time we actually showed that the second equation here, the equation for the energy, is a pretty obvious consequence of the formula for the wave function corrections, because K0 n plus 1 is P0 W R0 W to the n. Sorry, it is, I should say, it is P0 W psi 0 in nth order, and we know that psi 0 in nth order, according to the equation here, contains all the link diagrams, and it is easy to show that if you have link diagrams, that the only diagrams you can obtain by using an extra W are the connected ones. Okay, so what we did last time is this. We said, to prove the linked-cluster theorem, we defined the total wave function, which is of course the sum of various perturbative corrections. We said that we will define the total wave function as the sum of the linked contributions in all orders. We then define the total energy to be the zero order part of it, plus the sum of various corrections, where we compute these corrections using only connected diagrams from the corresponding principal terms. Okay? So we define our total wave function to be a sum of the linked pieces from each order, from all orders, and then we assume that the energy can be written as a sum of all the connected pieces in all orders. Okay? Now, of course, you know that normally, if you look at the perturbative expansion, corrections to the energy contain disconnected diagrams, and corrections to the wave function contain also unlinked diagrams. Okay? And they also contain renormalization terms, both in the wave function and in the energy corrections. But we are going to define psi node and k node without renormalization terms and without unlinked diagrams in the wave function and without disconnected diagrams in the energy. And we will show now that this psi node defined through link contributions and this K0 defined through connected diagrams satisfy the Schrödinger equation. So K0 plus W equal acting on psi 0 defined in this way equals K0 psi 0. This is what we want to prove. We will prove. this. Okay? All right. And in order to prove that this psi 0 and this k 0 satisfy the Schrödinger equation, okay, we started last time. We started our consideration last time by considering the expression where we have kappa 0 minus k 0 acting on psi 0. Kappa 0 is an eigenvalue corresponding to phi 0, the unperturbed eigenvalue corresponding to phi 0. Okay? And we demonstrated, after a few manipulations, that this expression equals sum over n from 0 to infinity w r0 w. You form the link diagrams from r0 w to the n, and then we use this extra w to form link diagrams with external lines. Okay, and all of this acting on phi 0. This is where we stopped last time. Let me make sure w r0 w to the n linked and linked with external lines. Okay, let me maybe briefly summarize how we ended up there. So what we did, we started with kappa 0 minus k 0 acting on psi 0 defined through link contributions. Okay, the equation that you see over here. The n equals 0 term can be immediately eliminated because n equals 0 gives you phi 0. Phi 0 is an eigenstate of k 0 with an eigenvalue of kappa 0. So we can start immediately, and that's what we did last time, by summing linked diagrams in all orders beginning with n equal 1. Okay? Then, because n is at least 1 here, there is at least one r0w here, then we decided to take r0w and write it, so split it from the remaining r0w's. So our next step was, last time, kappa 0 minus k 0. We wrote the resultant outside the summation. Then we have sum over n equal 1 to infinity. Okay, and then we have w r0 w to the n. Okay, we form link diagrams here, acting on phi 0. All right. And then we change the summation from n equal 1 to 0. Okay, because if I take one r0 and one w, and if I isolate them from the rest of this expression, then the summation over n will start from 0, okay, not from 1. So this was our sort of second important step. Okay, then we realized that because there is a resolvent here, resolvent has external lines. So because of having external lines that go this way, and because of having phi 0 this way, we of course immediately realized that these diagrams here have to be connected to the lines of R0, meaning that we have actually external lines in those link diagrams. Okay, produced by w r0 w to the n. And then we use the property that says that kappa 0 minus k 0 times the resolvent equals the projection operator of Q, the one on projection of the Q space, which is the identity operator minus the projection operator on the P space. And then we inserted this expression into our formula, obtaining two contributions. The first one is simply sum over n equals 0 to infinity. W r0 w, take the nth power of r0 w, okay, and then we have all link diagrams with external lines coming from this operator product, acting on phi 0, meaning that all the external lines will be extending to the left, okay, and then we said that the second contribution produces a 0 term, okay. I watched the video and I noticed that then I wrote the plus. Well, there's an obvious minus. I don't know how I wrote the plus. Anyway, you probably noticed that. Okay. I'm sorry about that. So when you see something, correct me. But anyway, the point is that we don't have to write anything further, because then you end up with phi 0 times an expectation value of this product, okay, in phi 0. You know, phi 0 product phi 0. But this product has external lines, and when you form expectation values in phi 0, there should be no external lines, meaning that the second term is simply 0. So that was sort of the next important step, I guess. And then we made one more change in this equation. That is, we said that, well, if you have linked diagrams with external lines here, then this part must be linked as well. That is, it's impossible to form a linked diagram with external lines if this part is unlinked. And this part can only be linked or unlinked. If it's unlinked, it has a vacuum part, and that W cannot eliminate that vacuum part. So you would end up with unlinked diagrams, okay? In other words, we can write one more equation. That was the last thing we wrote last time. Essentially, that is that this equals W R0 W to the N. Then we're forming linked diagrams from R0 W to the N. And then we use that extra W to form linked diagrams with external lines. Okay? So that's as far as we could go using these considerations. Okay? So this is the equation I have here. All right. And then I said at the end of the last lecture that it is hard to progress further along these lines. That is, we applied several tricks to get here, but it's very hard to go beyond this point. So instead of trying to force ourselves to somehow figure out what is this expression, we decided to say, well, okay, why don't we just try to consider the following formula. W acting on the sum from n equals 0 to infinity of R0 W to the N linked P0. Why would I want to do this? Because that's what I have here. I have W acting on linked diagrams of the R0 W to the N type. Okay? We certainly will obtain linked diagrams with external lines from this, but we can obtain other terms. And the point is that, as you will see now, it's very easy to interpret all those terms that will come up. Okay? And in this way, we'll be able to compute the desired expression, this one here, by forming a difference of W acting on this linked sum minus the other terms that will come up. Okay? That are easy to interpret. And we want to consider this one. This actually also is easy to interpret. That's another argument that we can use here, because you recognize that this part here, if you go back to our definitions of what psi naught is the sum of all the linked pieces. Well, that's what you have here. So this is phi 0 right away. So we know how to interpret this expression right away, okay? So this is useful. So now we have to simply, think about what can happen when you apply W to the sum of these linked terms. What is that W can do simply to those terms? Well, look, W has external lines, right? It's a perturbation vertex, written in the normal ordered form. Okay? It cannot connect, you cannot connect lines of W among themselves. You have to connect W. If you want to connect W to anything, you have to connect it to something else in the expression. So W can do two things in principle. It can close all the lines of this, or it can close some or none of these lines. Those are the only two logical scenarios. So let's start with the case where we use W to close all the lines, all the external lines of this expression. Okay, I'll write it maybe in words, terms will be writing. So let's write the first case. W is used, here, W is used to close all external lines of the linked terms R0 W to the N L. Okay? That's going to be the first case. And there will be the, yes? Something?
There are external lines in
Here.
this expression, right? So
Yes.
why are we considering this?
Because, as I said, I don't know what to do with this. I don't have a clear interpretation at this point to this one. So what I'm going to do addition to subtraction, okay? What I'll do, I'll consider this term. Of course, this will emerge as one of the contributions. But there will be other contributions, okay, which actually can be very easily interpreted. So then we'll simply calculate this as a difference. of W acting on all terms minus the other contributions other than this. Okay, that's what I'm doing. I'm trying simply to avoid pushing this any further because I don't really know what to do with it. You know, how to relate this to psi naught, for example, because that's our purpose. You know, we want to prove the Schrödinger equation. We need to find a way to extract somehow psi naught from it. There is no psi naught here. Okay, so we have to do this. Okay, so that's the idea. Good question, because that, you know, that's the trickiest part of this proof. Okay, so anyway, so as I said, we can do two things. We can apply W. We're applying W to this, and now W can be used in two different ways. Either W closes all the lines, or it closes some or none of the lines. So let's start with the case where W is used to close all the lines of these linked pieces. That's what I wrote here. W is used to close all external lines of these linked pieces. Well, you can think about it this way. Well, if you have a linked piece, then it is either connected, okay, so maybe you can even analyze this. So R0W to the n is either connected, or it is disconnected but linked. Right? Those are the only two logical choices you can make. Well, if it's connected, all right, well, of course, you know, the thing is what n, you know, if n is 0, then of course, actually, in reality, you know, you can start at n from 1, because the n equals 0 is the unit operator. I mean, not here. Maybe here. Here, n starts from 1, because if you want to use W to close all the lines, then you have to have at least one vertex, you know, to be able to do this. Okay. So what happens if this part is connected? Well, if this part is connected, I'll just sketch it. Okay. There's some sort of a block which is connected, and you take your W, and I'm going to illustrate it with the two-body W. W is used to close all the lines. So you know, if there are some external lines here, well, you can just close them. Well, this is connected. You're just forming a connected diagram with no external lines, which in our notation from the previous lecture is what we call C0, right? Connected diagram. I'm writing the type of a diagram. It's a connected diagram with no external lines. Well, what happens is if R0W to the n happens to be disconnected but linked. Well, then you have at least two pieces, okay? Both having external lines, okay? Because that's the meaning of the word linked. At least two, of course, you know, you can have more than two. Alright? And then you have your W here. W is supposed to close all the lines. Well, if it closes all the lines, then you will produce a connected diagram from this. Because that W, this is disconnected, but the W will connect to both. So it will make a connected diagram with no external lines. So you see, no matter what I do, if I want to use W to close all the lines, okay, then the result is always connected diagrams with no external lines. That's the first term, okay? So I'm going to start in these terms, maybe here. So we already know that the first contribution that will come out from the result of an action of W on this is an expression which looks like this, sum over n, okay? I write it from 0 to infinity because the n equals 0 term drops out anyway, so it doesn't change anything. R0W to the n, okay? You started with having linked contributions here, R0W to the n linked, and then we now determined that if you want to close all the lines, you end up with connected diagrams with no external lines, C0, okay? That's the first contribution that we can produce. Now I have to figure what are the other possibilities. What if W is not used to close all the lines? Right? Okay, well, let's talk about this now. Well, logically speaking, if you don't want to close all the lines, you can do two things. Okay? You can close, if you want to close some lines, you can close lines, you know, if you have a, linked means disconnected, okay? And among the linked diagrams there are disconnected linked diagrams, right? If you can use W then to close some of the lines by simply closing one of the pieces of the disconnected link term, right? To produce the vacuum diagram. That's one possibility. The other possibility is to close some of the lines, but without closing any of the pieces. Of course, the third case, the last case that I just mentioned, is what we are looking at, right? That's the case where we are using W to close perhaps some lines here, but in such a way that you do not produce vacuum pieces, because we're left with link diagrams, right? So I guess the case that is going to be the sort of different than this is the case where you use W. So I'm going to start writing this here maybe. Okay. Here. W is used to close the lines of one of the disconnected, one of the, say, okay, one of the connected parts of R0W to the N, disconnected but linked, okay, to produce vacuum pairs in general, right? Maybe I should say W is used to close the lines of at least one, because of course you can close more. At least here, at least one of the connected parts of a disconnected link diagram to produce vacuum pairs. Okay, that's the second logical possibility. Okay, what is this what is this sort of in pictures? Okay, so imagine that I have a disconnected link diagram. Okay, of the R0W to the N type. Okay, so I'm going to write it as disconnected link. Disconnected link means that you have externalizing both. But in this particular subcase, what we're doing, we're taking the W and we're using the lines of W to close one of the two pieces. So so let's assume that we have 4 lines here. I'm going to close these lines here, okay? And I will leave lines of B untouched, okay? So you end up with a diagram that looks like this. Okay, now I close the lines of one of the connected pieces to produce a vacuum part, and then the B is hanging there. Remember, B can be more than one part. It can be several components, right? Because it's all disconnected, linked, and it's very general. All right? That's what this case is doing. Okay, so here we are now, to summarize, in the previous case we used W to close all the lines. Now we're closing some of the lines, but we're closing them in a very specific way. We're closing them such that we are closing at least one of the connected pieces to produce a vacuum piece. Well, what is the result then? Well, this is an unlinked diagram. Okay, this is unlinked, but it has external lines because you didn't close all the lines. Okay, so I will put EXT. Okay, do I need to explain this, or it's clear from? UL stands for unlinked, EXT means that there are some external lines left in it. Okay? So if I want to write it mathematically, maybe I'll I'll write it here. That's going to be our second big contribution. It's going to be something that looks like this. Sum over N from 0 to infinity, then you have W, then you have R0W to the N. Okay? You started with link diagrams, and now I am using W to produce unlinked diagrams with external lines. Okay? That's what I just did. Well, what is the last option then? If I don't want to use the W to close all the lines, and if I don't want to use the W to produce vacuum pieces, I will use it to close some or none of the lines to produce link diagrams with external lines. Okay? So the third contribution is this one. That's the only other possibility. Use the W to close some or none of the lines here, but in such a way that none of the pieces is closed completely. So we are left with linked diagrams with external lines. Is this clear? It's essentially, going back to this picture, but not doing what I just did. Don't close any of the pieces. Maybe put a line here, put a line there, put a line there, but don't close any of the pieces completely. Well, that's going to be linked with external lines, okay? So logically, the third possibility, which is not this one is what we were sketching here, applies to this equation. The final case is the expression which we've been wandering around, which is W, R0, W to the N, okay? We take a linked diagram from R0, W to the N, and then we form linked diagrams with external lines. because we didn't use P0 to close lines of n of the pieces. Okay, is this clear? Those are the only three logical cases. Do I need to run it over again, just to make sure?
This top piece where you have unlinked external, you're just referring to the one on the right though, correct? Or you're talking about,
Sorry?
oh, so these are your two contributions from this,
There's the
two
third.
options from this.
That's when you don't close all the lines. This is when you close all the lines.
Okay.
Okay, so this is, so one, okay, well, let me summarize this, okay? That's the trickiest part. You just have to understand simply what can happen. And you have to make sure that we don't miss anything, okay, in the proof. So, I'm using W to apply it to this theorem. I can use W to close all the lines of these link diagrams. That's what I did here. And we figured that they must be connected diagrams with no external lines. In these two cases, I'm using W to close some or none of the lines. Okay? And I can do it in two different ways. I can close some of the lines in this way, producing this unlinked diagrams, because I'm closing some pieces completely. Okay? Or I am not doing what I'm doing here. That is, I'm closing some of the lines, or maybe none, to simply be left with linked diagrams. Okay? With external lines. That's the only thing I can do. There's nothing else left. So this means that now we have a decomposition of W acting on size 0 into these three terms. Okay? I'm going to actually call them A, B, C. Okay? Let's call this one A. Let's call this one B. And let's call this one C. And let's simply now try to interpret them. I said that we did all of this hard work because these terms can be now interpreted. Okay? In terms of where we're headed with these calculations. Okay, so let me then, I guess I'll erase this because this was just a summary of our last class. Anyway, okay, and let's see what we are learning. So what we learned is this. Maybe let me write it. W acting on the sum over n equals 0 to infinity, R0 W to the n linked phi 0, okay, equals A minus B minus C, okay? Where I define A, B, C on the other two blackboards, okay? We already know that this is easy to interpret. This is size 0, right? Sorry, I should write A plus B plus, what did I do? A plus, okay, plus B plus C, okay? All right. So we have to now we know that we are interested in term C, okay? So because, remember, we are interested in saying what? We are interested in this quantity, kappa 0 minus k 0 acting on psi naught gives us this term. That's what we now call C, okay? So I'll write it as C, okay? And we know that C equals this minus A and minus B, okay? So in other words, we have W psi naught, that's this term, minus A, I write it like this, minus B. Okay? Is this clear to everybody? What I'm doing? So as you can see, I'm doing what I said I'm going to be doing. I am computing term to term here, which we didn't know what to do with, as a difference of W acting on psi naught minus A and B, okay, which we determined from our analysis. Okay, so we can see now that in order for me to come up with some useful expression, I have to now understand what is A and what is B in terms of the wave function. Okay, and energy. All right, well, let's start analyzing this. Maybe I'll put it up, and we'll go through our analysis now. Okay. So let's start with the A part. Okay, what is A? Well, A, according to our calculation, is the sum over n from 0 to infinity. What you have there is W, R0 W to the n, okay, linked here, so we are forming link diagrams from R0W to the n. And then we are using W to close all the lines. So we are producing connected diagrams with no external lines, times phi0. Well, I think it's obvious to you now that I can drop the L. Why? Because if this part was unlinked, then you wouldn't be able to form connected diagrams. You know, if this was unlinked, you already would have some closed pieces in it, and the W would not remove them. Okay? So in other words, I can drop the L. That's what I'm going to do next. The sum from n equals 0 to infinity, W R0, W to the n. Okay? I don't need these anymore, so we just get rid of them. I'll just say form connected diagrams, okay, with no external lines, times phi0. But if you really go back to our, I erased most many of these equations, but if you go back to our notes, this is the sum of connected diagrams in all orders. So this part here, this part here, are sum of the connected diagrams in all orders. Connected diagrams that have no external lines. Well, connected diagrams that have no external lines means that you are computing really de facto the expectation value expressions here, right? This part here is nothing else than producing expectation value expressions from this part. Because, if this connected and it has no external lines. Well, no external lines means that's the number you're computing with. But then, if you add these numbers together, from n equals 0 to infinity, you end up with our definition of the energy. You remember, that's how we started our considerations. This part here is simply, when you add this stuff together, this equals K0 minus kappa 0, that's the number here, times phi0. Okay? So that's the meaning of A. Okay? You can see it has a very simple meaning, because that's how we define the energy to be. We define energy to be a sum of connected parts, okay? So we obtain it. Let's look at the B then. The B is the tricky one, or the trickiest one. Somewhere there must be a difficulty here, so that's going to be our difficulty. Okay, so what is the B then? Well, B is the situation where we use W, okay, to produce unlinked diagrams with external lines, okay, then acting on phi0. And then we have a summation here over n from 0 to infinity. That's how I define the B, okay? Well, let's try to, first of all, let's identify it's unlinked. Okay, if it's unlinked with external lines, I already drew how it looked like, but let's draw it again. Let's start drawing it again. So it looks like, okay, it looks like, say, some block A, block B, and we are talking about the situation where W closes at least one of the blocks completely, right? Where B has some external line left over. That's the picture we were drawing before, and let's have it again. Those are the kinds of terms we have here. First of all, if you are using W to close lines in A, then A must have at least one vertex. Well, if this has external lines, there must be at least one vertex here, perturbation vertex. That means that n doesn't actually start from 0, it starts from 2. There's at least one here and one here. Okay, one vertex here, one vertex here. So altogether, that means actually, okay, I'm going to keep that 2, that 0, but I will really say now that in reality the summation goes from 2, not from 0, because the n equals 0 and 1 contribute nothing to this term. Okay, well, so let's analyze this term. Remember, those are now unlinked diagrams. We spent the last few classes analyzing them, and we demonstrated that they always come in groups of time versions of the first kind. Okay, so anytime you have an unlinked diagram like this, you also have to consider all of its time versions of the first kind. Is it okay if I still use this acronym? TV1. Okay, that's what we really are looking at here. So we are looking at unlinked diagrams with external lines and all their time versions in all orders. That's what it means. That's how you read this expression, in all orders. Okay, so I'm going to now manipulate this a little bit. Okay? Maybe I'll keep this one still. Yeah, I'll come back. Maybe actually, I can start erasing this back. Okay? So maybe, okay, I will not do it. Let's keep this backward this way. So this is where we, okay, I can put this a little bit up so we can see the whole picture. Okay? I want to understand what's in the B there. Okay, what I'll do, I will do the following. I will actually start computing these terms, these various time versions. I will put arrows here, okay? So that's my next picture. I'm going to draw. So imagine that I have this A and the B, and I will have now bigger. Let's make it bigger so you can see it. I'm going to put arrows. Of course, I'm using a two-body perturbation vertex. I could have used one body as well. It doesn't matter, okay? I'm going to label them as A, I, B, J. And I will simply now say explicitly that we're summing this over A, B, I, J. Of course, we're summing this over all the other indices. I'm not going to now write those because we don't care about them. Okay? And then we have to consider this expression and all time versions of the first kind of it. Look, I can do the very simple thing. I can isolate this piece and I can rewrite this expression as a summation over A, B, I, J. This vertex written separate, but with the indices of the lines of A. So A, I, B, J times A here having exactly the same four lines. Okay, A, I, B, J, because they are ultimately connected. Okay? And I'm keeping all the denominators of AB. Remember, AB is the wave function part. It has denominators. Okay, all these denominators I'll be keeping in A and B. So what we have is A like this, B like this. Okay? And then I have to consider all time version of the first kind. Okay? So I'm going to put brackets. That's the equivalent expression. Is this clear? It's an obviously, I'm just taking, the vertex and I'm making this more explicit, So there's a matrix element of the vertex times all the other stuff. Okay. Now, this is the time where we can finally use our factorization theorem. Or factorization lemma. You remember we proved that this kind of situation factorizes. What we have here are linked diagrams and disconnected diagrams. So we have disconnected linked diagrams here, okay? And their various time versions. We proved that when you have a disconnected linked diagram and all of its time versions, okay, when you add all this together, then the denominators of this, some of the denominators of these various time versions will factorize. That means that this term factorizes into a product. All of this there factorizes into. First, of course, we have our perturbation vertex. I'm not doing anything to it. But this part here, from the factorization lemma, or factorization theorem that we proved, gives us a product of A times B, where lines of A are labeled A, I, B, J, because they must be the same as they were in the beginning, right? But obviously, I can now attach my W back to the A after factorization. Okay, so I can simply write it as a product of the A, okay, times B. So in this way, I demonstrated that all the unlinked diagrams of external lines that contribute to our expressions factorize in this nice way, because of the fact that we can organize them in time version of the first kind, and we can apply the factorization theorem. Well, now we just have to understand what is A and what is B. Okay? Well, that's not very difficult to understand, because you always have to remember that we are doing this work in all orders. So, and A, B are just parts of the unlinked diagrams we are considering in all orders. Okay, so let's start with an A. Well, A, according to the analysis we did there, was obtained by doing the following: by attaching the what we're doing here, we're attaching perturbation vertex to something which is linked. A itself is linked. Right? A, that part here, so if I write it as perturbation vertex attached to A, let's sort of write it very explicitly, okay? Well, I did just a moment ago. This must be linked, because A is part of the link, and those are actually all linked diagrams, because you remember, we're talking about an infinite order calculation. We are looking at not just one diagram, those are all diagrams in all orders that look that way, meaning that both A and B are infinite order expressions containing all diagrams. So what we have in A are all linked diagrams, okay, of this type in all orders. That's what you see there, okay? Of course, with n being greater or equal 1, because there's at least one vertex that you connect to this. So n cannot be 0. If you have n equals 0, there will be a unit operator, no lines in it. Okay? So this means that if I now attach W to the link, remember what happens. When I attach W to the link diagrams, we end up with connected diagrams. And since I'm closing all the lines in that A piece, I end up with connected diagrams with no external lines. So this is nothing else than P0, W, R0, W to the N. Okay, you take linked and you connect completely, producing no external lines in this A piece, and you sum this over N from 1 to infinity. Of course, I can extend it to 0 because I would not produce a connected diagram from, expectation value of W. So, in principle, start from n equal 1, but if I put n equals 0, I'm not making any mistake, because if n is 0, then you have some W. W cannot form a connected diagram. It will be just a 0, right? So you can keep 0. All right? That's what it is. But what is it? This is simply K0, according to our definition. Those are all connected diagrams in all orders. Well, that's K0 minus kappa 0, right? Because we already said that we can drop that L. Okay? We said it already at least twice. Okay? So we know what is the meaning of A. When you look at, if you look at one diagram, of course you wouldn't be able to do this, but I'm looking at all diagrams that look that way in all orders. So the A piece adds up to the energy. Well, what about the B then? Well, it's very similar. If you think about the B, remember we're talking about all orders. That's the sort of thing that you always have to keep in mind. We're talking about, again, B must be linked, because B is part of the link. B is part of, well, not that one, of this one, of the link, right? So if you add, this is in all orders, so you look at link diagrams in all orders that have external lines. So what you have here, okay, are R0, W to the N. You're talking about link diagrams in all orders. Okay, we're acting on phi0, lines are extending to the left. Okay, and in all orders, starting with 1. I don't start from 0, because if n equals 0 would mean no lines, no external lines. So the first term that you see there is n equal 1. But we know how to interpret this guy. You see? This one is simply the total wave function size 0 minus the 0 order contribution to it. Because we are not including n equals 0. So you see, the second term, although it looked initially sort of complex, I'm talking about the B term here or here, it really factorizes into because we're doing this work in all orders, all these unlinked diagrams with external lines originating from the linked pieces, okay, produce at the end a product of A, which is the energy, times B, which is the wave function, which is a wave function minus the 0 order part of it. Okay? So now we know what B is. Well, so I guess we're in good shape, right? Because now if I go back to our calculations, we know what A is. We wrote the formula for A. We wrote the formula for B now. So let me maybe summarize this information. I'll put this up. I'll go back to the blackboard I was processing here. We just proved that A is here, K0 minus kappa 0 times phi 0. Okay? the B part, as we just demonstrated, is a product of A times this B, which is K0 minus kappa 0 minus this and this the wave function difference. Okay? So that's K0 minus kappa 0 times psi 0 minus phi 0. Okay? So I guess now we've got all the pieces of the puzzle in front of us. Now what we need to do is to see what comes out. Okay? Do you have any questions to this part? Because right now the end is easy. Any questions about anything that I said so far? Remember, none of this would be possible when we were doing some finite order or one of the diagrams and so on. We are doing these factorizations because we are adding all orders. Okay? So of course that means that factorizations happen completely. You know, the way they did it. So with all of this, I guess I can conclude by, let's see, I'm going to now put this up. Okay? I think I can erase now these definitions because, did you copy them? All of this information? Okay? So I'll erase now these things. And let's see, what do we get? Well, on the left-hand side, we have kappa 0 minus k0 acting on psi 0. On the right-hand side, we have w psi 0, which was w acting on all the linked pieces, as you remember, minus a, which is minus k0 minus kappa 0 times phi 0, minus k0 minus kappa 0 times psi 0 minus phi 0. Okay? That's the A term, that's the B term. Okay? You can see there are cancellations here. You can see that k0 minus kappa 0 times phi 0 comes here with a plus, here it comes with a minus. So I can eliminate this whole term and cancel this phi 0. Okay? Now, let's continue rewriting. So on the left-hand side, I have kappa 0 times psi 0, I'll split it, minus k0, the capital K0, the operator, acting on psi 0. On the right-hand side, I have w psi 0, okay, minus k0 times psi 0, k0 psi 0, and then there is minus and another minus, that's a plus, kappa 0 k0. Sorry, kappa 0 psi 0. Okay? And now you can see there are cancellations in this equation. There is kappa 0 psi 0 here, and there is kappa 0 psi 0 here. They do cancel out. Okay? All I need to do now is to rearrange terms. And you can see I end up with k0 plus w acting on psi 0. Those are these pieces here and here. Gives me k0 psi 0. And that means that I showed that our psi 0, which consists of link diagrams only in the wave function, and our k0, which consists only of connected diagrams, they satisfy the Schrödinger equation. Which means that they must represent the exact solutions. Okay? Meaning that psi 0 indeed is a sum of corrections. Okay, so this means that psi 0 is a sum of corrections, but we do not consider in these corrections all diagrams. We only consider linked diagrams from the principal term, and we don't even have to, we don't even look at the renormalization terms. We don't have to worry about that. Okay? And then since we define k0 as a sum of the connected pieces, then we know now that we can compute the energy as the unperturbed part plus some of the corrections, and in those corrections, let's go from 0 to infinity here, from 1 to infinity, we only have to consider the connected terms originating from the principal term in perturbation theory. Okay? That's the end of the proof of the linkage-Castle theorem. All right? As I said, historically, this theorem was first observed, like we did in this class, by looking at the fourth order. Okay? This was done in the famous paper in 1955 by Brueckner. Okay? And I attached these classic papers to the blackboard. You can just go and really see how this was done. It's not going to be done exactly as we did it, because you will see the resolvents were not written as R0s. There will be other things, right? But the essence is the same. Okay? Brueckner noticed that you don't have to consider renormalization terms. You just have to consider link diagrams. So he had this idea, and you can see in the title of his paper, linked expansions. Okay? The word linked is already used there. Okay? He called these actually linked diagrams also irreducible terms. Okay? So we'll use various other names that we don't use anymore. Okay? And then Goldstone in 1957 took that sort of linked expansion of Brueckner, and he showed that this is true in everywhere, in all orders. Okay, that's 1957. And that's the paper that also uses Goldstone diagrams. Okay, Goldstone took Feynman diagrams and he adopted them to the many-model language, and we nowadays call them Goldstone diagrams. Okay? All right, so now, I guess, maybe we'll have a little break now, okay? So after the break, I would like to discuss consequences of this, of the linkage-Castle theory. Okay, one of the consequences is obvious. It's an easier theory than we thought in the beginning, because we don't have to worry about knowing renormalization terms in it. You know, you may have to know renormalization terms in some other applications of perturbation theory, but not here. They're gone. All you need to do is to draw linked diagrams in the wave function and connected diagrams in the energy that originate from the principal terms. But you know, the linked diagrams are a subset of all diagrams, and connected diagrams are a subset of all diagrams. Okay, so not only that you don't have to think about renormalization terms, you can only focus on the subset of diagrams. Well, which means that this theorem provides you with a nice sort of help, right? It really facilitates your work. So if you go to some, say, fifth order or something, you're not going to be drawing all diagrams for the energy, right? Fifth order energy will be drawing only connected diagrams from 5W vertices, okay? No renormalization terms. So no use for bracketing technique, I'm sorry, right? But the bracketing technique was needed for us to simply see that this concept is okay. Right? Without it, it will be all an ad hoc statement I will make. Okay, so that's where we are. But there's another consequence which is very important for our next topic, which is the concept of size-extensivity. So let's have a little break until, say, 1:30, and then we'll resume. We'll talk about size-extensivity next. The rest of the notes. Huh? Yes, they are. So I'm saving it. They need to print this. Right? Let's see. The other has it. Yes. That's what we call this. I did, right?
Yes.
So you got my message, right? Done? Did you get my message? Right. And you? Sorry? The message about the final exam?
Yeah.
Yeah, okay. So you know it's next week here at, on Friday. Next week at 2 o'clock. Okay? I'll look at that back here. Let's see. Also, okay, Josh. You didn't get this from the rest of the lecture notes. Cool. You will not need all of them because we will stop it at some point. As I mentioned actually in this email, we're planning on the next lecture on Monday. Extended one. Of course, it's all. I mean, you don't have to attend it if you don't have time or something. That's right. But we will record it. Nicole has kindly agreed to do this, and there will be. I'll talk about Kappa-Castro theory. Some details of Kappa-Castro theory. That's the idea. Cool. So I guess we'll know more about the time, exact timing, I guess, on Friday. We have this room here reserved for the whole. I think it's a 4-hour block. Like nobody's using this room in the mornings. We'll take advantage of that block. We don't have to, but I guess we'll start maybe at 8:30 or something. Go. Okay, so I guess let's talk about the size extensivity. So we'll now demonstrate that any finite order MBPT calculation leads to a size-extensive energy. And of course that implies typically all properties of a system that can be obtained by differentiating energy. If you can differentiate energy and define, say, a dipole moment by doing this, of course that extensivity will be retained. Okay? So size extensivity here will be understood as the proper dependence of the energy on the system size in the non-interacting limit. What we normally expect is that if I have an energy of an ensemble of, say, n non-interacting species, then the energy should be n times the energy of each of these pieces. That's what the word, like in thermodynamics, that's what extensivity means, right? Your property is extensive. Okay? As you will see here, the term connected diagram is very closely associated with the concept of extensivity. What we'll prove now, or what we'll do now, we'll analyze simply connected diagrams of, say, this type, WR0W to the n phi 0, which we know now define MBPT corrections to the energy, okay? But I will actually make this analysis more general, okay? Because I want to also learn a little bit about what I need for Kappa-Castro theory. So, when you have connected diagrams of, from the point of view of the sort of their topology, I can also consider other connected diagrams, okay? As you will see, probably today, okay, you can also consider connected wave function diagrams. Of course, wave function contains more than just connected diagrams, but among the linked diagrams, there are connected ones. Okay? As you will see, they actually define the cluster operator that we use in Kappa-Castro theory. Okay? So this means that it's worth considering connected diagrams in general, not just connected diagrams in the energy or not just connected diagrams in the wave function, connected diagrams in general. Because we'll learn now that anytime you use connected diagrams in your expansions, you end up with a size-extensive description. Okay? That's the sort of important statement. Much more general. But of course it has consequences on MBPT, which uses connected diagrams in energy. Okay, so in order to do this, imagine a situation like this. I have a system, and I'm going to fragment this system into pieces, say A and B and so on. I'll write it sometimes as sum over fragment C. Okay? So you know, you have fragment A, fragment B, fragment C, and D, and so on, however many you want. Okay? And we are interested in the non-interacting limit, which is the easiest way to accomplish the non-interacting limit is simply by setting distances between fragments at infinity. Okay? That's the way you can accomplish the non-interacting limit. In that non-interacting limit, the Hamiltonian of the system becomes the sum of the Hamiltonians of isolated pieces. Okay? Alright. We would like to understand what happens to connected diagrams in that limit. Okay. First, in order to define a connected diagram, you need a basis set. Spin orbitals, single particle state. So far, we just said, okay, P were our spin orbitals. But you know, when you have this non-interacting limit, you can simply build your basis from spin orbitals on the non-interacting fragments. So you can have spin orbitals here, defining this fragment. You can have spin orbitals here, defining this fragment. You can have spin orbitals here, defining this fragment. I will label them with an additional letter. So A, B, C will be telling you which fragment a given spin orbital belongs to. Okay? So I can build the basis set simply from product states, from states belonging, not from product, from states belonging to these various fragments. So PA, PB, PC, and so on. Okay? They may not be orthogonal, so there are two comments about that. They will be orthonormal typically when you produce, they will be orthonormal within the A, they will be orthonormal within the B, they will be orthonormal within the C. They don't have to be orthogonal, between themselves, because there may be overlaps. So there are two things about that. You can perform the so-called symmetric orthogonalization of Leptin to take care of it. Or in our case, actually, we don't even have to worry about this because we're really looking at the infinite separation. In the infinite separation, remember, we're not looking at finite distances here. In the infinite separation, if I take a product of, say, spin orbital psi PA, okay, say with a star, and psi, I don't know, say QB, okay, if I take that product, this product, then if the distance between A and B is finite, of course I may end up with a non-zero result. But if distance between A and B is infinite, then this expression goes to 0. Okay? In this limit. Why? Because psi PA is localized on A. Meaning that this orbital is sort of non-zero in the vicinity of A. Okay? Which means that X has to be close to A to make a non-zero contribution here. Right? At the same time, the same X are coordinates of a fermion, right? Coordinates of a single fermion here must be close to B. So in other words, you cannot be in both places at the same time if those places are separate by an infinite distance, which means that this expression is 0 asymptotically, right? We call this in chemistry, actually there's a term for it, zero differential overlap. Okay? Situation. That's an old term. It goes back to semi-empirical theory. Okay? So if this happens for every x, of course, if you integrate this over, you end up with a 0. If you integrate over the fermion coordinate, right, you end up with a 0. And that means that we have orthogonality guaranteed in the limit. Okay? Not for finite distances necessarily, then you have to do some tricks. But in infinite limit. Of course, this is only one possible design. I'm not saying that's the only design. Of course, someone may decide to produce delocalized orbitals even in the limit. Okay? If you solve Hartree equations, say restricted Hartree equations, and if you don't pay attention to this, you will end up with orbitals which are delocalized. Like the famous H2 molecule, right? An S orbital here, S orbital there, you add them up, that's a molecular orbital, and it's, you always mix them up even at the infinite distance. Okay? But I can always design my basis in this way. That's the point. And there are numerical ways to do this. Of course, you can do it ad hoc, as I just did. Okay? You can do it by performing numerical calculations by using, for example, techniques called localization of orbitals and fragments. All of this is okay. So we have this. So let's see what happens then to connected diagrams in this kind of a description. Imagine I have some connected quantity lambda. I'm not saying what it is now. Some connected quantity. How the connected quantity looks like? Well, I draw a sort of a diagrammatic representation of it. I'm going to use Goldstone representation for now. Okay, so that it is sort of easy to analyze. Okay, I'm just going copy from my notes. That's fine. Okay, so I will have a bunch of vertices connecting all these lines, right? So the final diagram is connected. Okay? Maybe here. And this goes back, it's some order. I'm not saying which order, I'm not saying anything specific, I'm just saying, okay, that's a connected diagram. Connected means that any 2 points in the diagram can be connected with a path inside the diagram, right? Like you can walk from one point to another inside the diagram, right? What I'm going to do now is, so this is a typical connected diagram, right? What I will do now is, I will pick up one specific vertex. Let's sort of look at this one here. But this is an arbitrary choice. I'm not saying that this vertex there's anything special about it, okay? I'm just picking up one vertex, okay, in an arbitrary way. I'm going to put arrows here around it. They are not particle lines, okay? They don't have to be, they can be, I don't care, right? I'm just drawing some lines, so don't read them as particle lines, I just have to put some lines, okay? So I'm not going to use our symbols A, B, C, I, J, K for them. I'm just going to label them as normal, in a normal way, as we always do. P, when the indices are generic. P, Q, R, say S, okay? This would be, and then you would normally have to sum, okay, over P, Q, R, and S. That would be a normal situation. But here we're talking about this non-interacting limit, where P, Q, R, S are localized on various fragments. So let's assume that P is localized on fragment C, Q is localized on fragment D, R is localized on fragment E, S is localized on fragment F. So I also have to add these indices here, C, D, E, F, and then of course I have to sum over fragments, C, D, E, F. Of course I may have to sum over more, so I'm going to put some dots around all of this, okay? Obviously. Right? But I'm just right now picking up on one specific vertex, and I want to analyze it. Okay? So what you see what I'm doing, I am summing, I'm writing this connected diagram as a sum over various indices that label the lines, but these lines are now labeled by indices that are assigned to various fragments that we have in a system. Okay? So in principle I have sort of a 4 fragment in the worst case scenario when C and E and D and F are different, I have a 4 fragment or 4 center sort of situation here. Well, let's look closely at this matrix element, at the matrix element behind this vertex. So what is it? It is P, C, outgoing lines, P, C, Q, D, interaction, R, E, S, F. Okay? Well, let's write it more explicitly. I'm going to choose V to, of course, that, the explicit form depends on what V is. Okay? We are going to assume here that V is such that it vanishes when the distance between particles goes to infinity, which is a natural behavior. So I will write this matrix element for a Coulomb interaction. Okay, it doesn't have to be Coulomb. Okay, so don't worry, it applies. What I'm doing here, it applies to nuclei the same way as it applies to anything else, as long as the potential vanishes at infinity. Okay, but I'll write it for Coulomb so that we have something specific. So it is sort of more. You can treat now these fermions as electrons in a molecule, interacting via a Coulomb law. So it's going to be an integral of psi p c star electron 1, psi q d star electron 2, psi r e x1, and psi s f electron 2, divided by the distance between these electrons, and of course integrated over coordinates of particles. Okay? So x, as you remember, x means x, y, z coordinates of an electron and the spin. Okay, so x1 means r1 for the spatial part and the alpha or beta spin and so on. Okay, let's analyze this expression. You can see that this expression contains these pairs of spin orbitals that correspond to the same particle. So you have here x1, x1 here, and then there's another pair here. Okay? x2, x2. Let's write these pairs and let's think about them for a second. Okay, so what? I'm going to write psi p c star x1 times psi r e x1. Okay, that's one pair that I see there. Okay, the second pair that I see is psi q d x2 star times psi s f x2. Okay? Now, just like in the previous consideration that I did already. You see, when C and E are different, those centers, C and E, are different, then in the limit of the distance between C and E approaching infinity, this term is 0. Why? Because if you think about it, you have the same electron here and here, right? So from the point of view of C, okay, in order for this function to be non-zero, okay, to produce a significant contribution, the R1 must be close to where C is. On the other hand, R1 must be close to where E is. So if C and E are separated by an infinite distance, okay, you will end up with a 0, because you cannot be in both locations at the same time. Okay? So this is again this sort of illustration of the zero differential envelope principle, right, in the infinite separation. The same applies here, right? I think we agreed that we have electron 2 sitting on 2 centers. If these centers are separated by infinite distance, that this expression produces 0 in the limit of distance of between D and F approaching infinity. Well, this means that I don't, in my summation here, I don't have to sum over 4 indices for the centers. I have to sum over 2 only of them, because based on these considerations, we can assume that centers C and E are the same, and centers D and F are the same. Okay. Well, let's then rewrite our matrix element for this situation. Okay. So what we have is an integral. We'll have psi p c star x1, psi q, now I'm going to say, okay, it's qd x2. Then now I'm going to say psi r, not e, but c, because e has to be c or we're getting a 0. Okay, so c x1 and then psi s d x2 divided by r12. Okay, and integrated over both parts. Okay? That's where we are now. Well, let's think about this expression. Well, you can see that if I say pick up on this term, this function, from the point of view of this function, which is localized on C, x1 must be somewhere in the vicinity of fragment C. Okay? Because these functions decay. Alright? From the point of view of the center D, x2 must be in the vicinity of fragment D. Okay? Maybe I'll write it not x1 but r1. Okay. Let's put arrows. Put arrows there. I didn't. Okay? Well, if r1 is around C, okay? So if R1 is around, say, C, and R2 is around D, okay, there's a D somewhere, at infinite distance from it, okay? Well, this means that in order for this, in this expression, the R12 approach is 0, okay? That is, the R12s that contribute to this expression are going to 0 because we separated the fragments. Okay? So this happens when C is different than D, and the distance between C and D approaches infinity. Okay? That is not true, of course, for any finite separation between fragments, and that would not be true if the psi functions were, I don't know, plane waves. But we're talking about the basis set for the bound state. So they are all behaving like sort of Slater or Gaussian bioorbital, so they vanish quickly, right? Exponentially quickly, right? So that will happen. So that means that this expression will be 0, okay, really, unless you say, so this really vanishes, unless C and D are the same centers. See, but if C and D are the same centers, then the only matrix elements in our diagram that contribute will be PC, QC, V, RC, SC. Okay? That is one center or one fragment integrals. Where when we started with 4, possibly 4 fragments, we're down now to a sum over single fragment expressions. You have a question?
Is that a limit? Did you write something?
Yes,
wrong?
what do I do?
Shouldn't R12, wouldn't that go to infinity if the radius between C and D
Oh.
is infinity?
Yeah. Thank you. We don't want to go there. The other will be called cusp conditions. Yeah, that's a different story. Okay, sorry. Okay, thank you very much. Yeah, that's what I meant. Yeah. So in other words, yeah. So when R1 has to be around C and R2 has to be around D, that means that the distance between 1 and 2 must go to infinity, and that's exactly what Max said I should have done. Okay, good. All right. So with all of this, if I go back to my schematics here, okay, you can see that this picture can be greatly simplified in the limit we are considering. Okay? I don't have to sum over 4 fragments for a particular vertex. I can just sum over, okay, maybe I'll write it here. I can sum over, say, C for this particular vertex. And then all the 4 indices belong to the same fragment. So you have PC, QC, RC, SC. And then our picture will be exactly the same diagram we looked at. Okay, so I'll try to copy it. That's right. Okay. So it's now exactly the same type of a diagram, except that now we have PC, RC, QC, and SC. Okay? So in other words, we are summing over diagrams of the same type, but using spin-orbitals of 1 fragment at a time. See what happened? A connected diagram has this feature that when you go to the infinite separation of fragments, okay, then connected terms split into connected terms of the same kind. The lambda c is what you see here. It's the same diagram we started with, except that I relabeled the lines to be sitting on the single center, right? In each case. So for connected diagrams, we have this feature that the connected means size extensive, because what it means is that you end up with a proper behavior. Okay? Connected diagrams split into connected pieces, connected diagrams of the same kind sitting on non-interacting fragments. Okay? You can see by the same token that disconnected would not be good. Because if you have disconnected, then each connected splits like this. But when you have disconnected, you end up with products of connected pieces. Okay? That means that each connected piece has a proper scaling with the system size, right? But the product of them will not. So if, for example, if I have an ensemble of n hydrogen molecules, okay? Imagine that. And if I want to know the energy of it, okay? If that energy, we know now that energy contains only connected diagrams. Because it contains connected diagrams, then you end up with n energy of a single H2. Okay, because of this property. Simply connected, and the connected diagram becomes the sum of connected pieces. Okay, so in this case you have an ensemble of n non-interacting, of course that means non-interacting. Then you end up with this expression. Of course, you know, the E contains 2 parts, the Hartree-Fock part, if I use Hartree-Fock, for example, reference, and the correlation part. Hartree-Fock is size extensive, that's easy to see. So the one you have to focus on the correlation energy. Well, we know that the correlation energy is the sum of corrections from MBPT. Okay, and they are all connected, so they're all, you know, they're all splitting into sums of diagrams like this, which means that we have this behavior. But imagine that my energy contained disconnected diagrams. Well, if it did contain disconnected diagrams, in some calculation, then I will not have this property. Okay? That would not happen. Because you will end up with terms which scale as n squared. You know, for all those disconnected diagrams of 2 pieces. Because each piece has an n is proportional to n. So you have connected diagram of 2 pieces, each one of them is proportional to n, so you end up with n squared. You have connected diagrams of 3 pieces, each one of them, according to this derivation, will scale as n, so you have n cubed. So you see, you start obtaining some strange behavior. And you may think, well, this is never happening. Well, it does happen all the time if you use CI. If you use a CI approach, truncated CI approach, okay, whether it's single reference CI or multi-reference CI, as long as it's truncated, so you don't use full CI, okay, or if you don't do some tricks like a posteriori tricks, correcting this stuff and so on and so forth, if you don't do this, you end up with energy expansions that contain disconnected diagrams, and that means the results of truncated CI calculations are not size extensive, which means that you will end up with a wrong dependence of the energy on the size of the system, which actually is an error, which is not because your computer is too slow and you can't do work on it. No, it's because you have terms in your energy, okay, that do not cancel out. That's not what happens in the way in MBPT. You have a question, Mike, right? Or
Yeah,
something?
so lambda C here corresponds to
The
this,
same picture,
this whole connected diagram, but restricted to the fact that each vertex has the same
same fragment.
fragment.
Yes, because this propagates. Yeah, I guess I assume that maybe it's not as clear, but maybe I should emphasize. Of course, I did it for one vertex, but you can see if this line is PC, you go to this vertex, that means that this is also P. This is also on the C. This is also on the C.
Okay.
So this
every
information
vertex
spreads
is
all over
gonna
the
be
entire
C.
diagram.
Every vertex is going to be a C.
Yes, yeah, because I picked up one.
Because
But I said in the beginning, in an arbitrary way. Okay? So this happens to this vertex. Of course, now you see this line goes, it's connected. Remember, because it's connected, this line will now go into this vertex. This is now C. So this one also is C, and this is also C, this is also C. So all four lines belong to the C now, again. Right? And you continue walking through the diagram. It's connected, that's why. So you go here. That's the line that belongs to the C fragment. So now this means that through this vertex, these lines belong to C. And then these lines belong to C. All the lines belong to fragment C. So it means that a diagram becomes a sum of diagrams of the same kind are written for individual pieces. Is this clear? That's what the word connected is. Because you see, connected means that you're never able to stop this walking through a diagram. You can only stop walking when you're done with the whole thing. Walking through all of it, right? So connected diagrams have this property, meaning that you would end up with something like this. So in general, maybe I should say that when we go back to our MBPT, okay, these equations here, you see we have connected. So this means that if you look at any correction to the energy in MBPT, in any order you like, second or higher, any order, then because it is connected, the results of finite order MBPT calculations are size extensive. Okay? What's going to happen to the energy in any order is what happens in this diagram here. What will happen, I'll put this up. The energy in say order n plus 1, maybe write it, will become an energy in order n plus 1 on fragment A plus energy in order n plus 1 in fragment B and so on. Okay? Because each of these terms are connected. Okay? Yes?
You might have said this already, but this only applies if you're using orbitals, right? Not if you're using plane waves. That's your basis.
Yes. Well, connectedness is still there. So, actually, the argument would be different. No, so these results do not depend in the end. They, so it is like this. I try to give you an argument that convinces you, okay, that extensivity is guaranteed through this analysis of non-interacting fragments. But of course, extensivity, the proper definition of it, is that theory is size extensive when it uses connected diagrams in energy. Okay? Now, so then of course you could choose other basis sets and you would have to use other sort of manipulations, right? But it is true that the easy way to see it, I guess, is through the analysis, right? I said there are some fancier ways to do this, but I will, there are ways to analyze diagrams in terms of their end dependence, for example, right, and so on and so forth. And I didn't do it here because it would be lengthy and would not really change the conclusion. Okay, but anyway, so those are size extensive. And they are size extensive because we have the fact that the connected diagrams split into connected contributions from different fragments if we look at the non-interacting fragment. Okay, so in other words, what you would do by writing these pieces, K0, n plus 1a or b and so on, this would mean writing an expression which would be phi0, w, r0, sitting on the, all written in terms of the, let's see how I have it. So you'll have to simply, maybe I write it like this. You'll have phi0, a, So fragment A, you would write here W, of course, corresponding to perturbation in the A, because we're assuming that there are no interactions between fragments, so the W also becomes the sum of W's. Okay, everything splits essentially, right? Then you have a resolvent written for say fragment A. I guess I put an A here or something like this. WA. Okay, you take it to the nth power, and then you take I guess connected. And P0A, that would be the correction in the order n plus 1 for fragment A. You will write similarly for B. So everything here uses spin orbital information from fragment A, okay? And this perturbation A is simply part of the perturbation corresponding to the A part, because there are no cross terms because we are talking about the non-interacting limit. Okay. But there's one problem here. Well, I would say there are two problems. If you really think about non-interacting limit, okay, there is one more requirement that I haven't discussed yet, which is the proper factorization of the wave function. If I have a system AB, say, let's assume, something like this, splitting into A and B, then we know that the energy, for example, should become a sum of energies. That is clear to us, right? The energy of AB should become an energy of A plus energy of B if this separation goes to infinity, right? Okay, and MBPT guarantees this behavior, okay, with the proper choice of reference and all that. But there is another aspect of it, namely the wave function of AB, okay, let's write it this way, should become the product of wave functions of A and B, okay? At the same time. That's what has to happen at the same time in the non-interacting limit. We'll talk about it some more when we talk about couple customization, okay? Well, that MBPT does not lead to. So MBPT is okay for energies. It is size extensive, so it has a proper scaling of energy corrections on the size of the system, but wave function, and if we still have it, that's why I erased it. The wave functions, remember, contain the linked diagrams. So if you stop at, say, second order or third order or any arbitrary order you want to stop at, you will have linked diagrams, but those linked diagrams do not add up in such a way that you can form a product of, say, linked diagrams on A times linked diagrams on B. Actually, it's easy to see. Linked diagrams on A times linked diagrams on B, you will have, like, say, connected times connected. Well, that's disconnected, okay? Now the question is, how does this behave? Okay, so the linked finite order MBPT expansion for the wave functions do not behave properly. They're useless, actually, for the wave function. So if there are any if there's any property that feels that behavior, it will not be properly described. Okay, and there are such situations. So MBPT has this problem, and this means that we have to talk about this. And as you will see, I was hoping to do some of this today, but anyway, on Friday and then Monday, we can show that if I define a cluster operator by picking up all connected contributions to infinite order, then I can demonstrate that the total wave function, which is obtained by adding all the linked diagrams together in all orders, can be written as e to the t acting on the reference determinant. Okay? That's what we'll prove next time. This statement. That's the so-called connected cluster theorem, which was proved by Hubbard in 1957, and you see it also in the paper by Hugenholz in the same year. Okay? So, and this form of the wave function guarantees this behavior. Okay? So the couple cluster, this will be a basis for the couple cluster theory, and the couple cluster wave function, because it's obtained in a different way, it's obtained by adding up linked diagrams to infinite order, and then factorizing into this exponential form, then the wave function has a proper fragmentation behavior. Okay, we call this actually a separability condition. Okay, an exponent for the system becomes an exponent of subsystems. Okay, at the same time, it is also size extensive because it emerges out of MBPT as an infinite order summation. So couple cluster theory is both separable and size extensive. Okay, MBPT is only size extensive; it's not separable. Okay. So we'll talk about it next time. Well, one thing I would like to say at the end is, okay, we have to continue on Friday. I would like to say this. There's one homework problem, last homework problem, okay? that would require a little bit more of my explanation. I haven't done it yet today. So in all fairness, I was thinking that I'll extend the deadline, because we'll still talk on Friday, if that's okay with you. That's how MSU students said. You know, if you don't want, the alternative is that you don't solve the last problem. You have to, and then you give me your homework back on Friday. But what do you prefer? I was thinking about extending, I would send an email, of course. I would extend it and say till Monday, and if you want to bring it to my office, that's fine. If you don't want to do it, then just email it to me as a scan. Do it again, do it as well. Please try to do it by, say noon or something like this, because I would like to release the solutions as well, right? So do you have enough time to look at the solutions before Friday? Okay? Is this a good solution, or you prefer some other way? I'm trying to be fair to everybody, and there are only two ways I can solve the problem. Okay, yeah? So please, let's assume that right, noonish, Monday is your deadline, and bring your homework to my office if you like. Or you can come to this class on Monday class, here or email it to me. Either way. Okay? So thank you very much. I'll see you on Monday.